Yeah, am I audible? Yeah, and screen is visible. Yeah. Yeah. Very good morning. Okay. So I think we can start the lecture. Okay, I think you have already gone through the recent recorded lecture, and I think you have seen the example there, which I have left for you at the end of the previous lecture. Okay, and okay, so here one definition, I think that also is, if you have seen the recorded lecture itself, then this definition is also was mentioned in that. So it is defining some definition. Okay, so it is such that you have an alpha, means alpha is any value between in this interval 0 to 1. And so Z is here is because you are talking about the standard normal variate. Okay, and I hope you remember what do you mean by standard normal variate is Z follows the normal distribution with mean 0 and variance or standard deviation is 1. Okay, so in that context, this is here is Z. Okay, and this suffix alpha here because to show the dependence. Okay, means for this alpha there is some Z alpha to show this. Okay, right. So if this Z alpha be such that, or G is such that probability of Z after this Z alpha is like, if you, I think I have here, or okay, if I look at here, this standard normal variate, okay, which is going to be a bell-shaped curve. Okay, PDF is a bell-shaped curve which is symmetric about the mean, that is 0. Okay, so it's not completely exactly a bell-shaped curve. I think that you can excuse me for that. Okay, so it says that alpha is any number 0 to 1. Okay, and you are able to identify a Z alpha. Okay, means it may be here or it may be here. Okay? Such that Z alpha. So this probability of this Z greater than Z alpha is equals to this alpha. So you are able to identify a point on this axis, okay, that real axis, such that afterwards the area covered is alpha. Okay, this is what it means. Okay, or in other words, it is if you try to write this is alpha, then what is 1 minus alpha is, this is this phi of Z alpha is 1 minus alpha. Okay, so this is here is you have this is this area is given by this. Okay, and this rest area is going to be given by this. Okay, so now you have the definition. of a percentile here. So we call Z alpha, okay, which is distinguishing these two things, okay. The 100, we call this Z alpha, the 100 time 1 minus alpha. So if you multiply it by 1 minus alpha by 100, it will become a percent, right? Yes, right? So 95% or 25% or 30%, okay? So this is something like that. So we call this Z alpha the 100 time 1 minus alpha percentile of the standard normal variable. So what does that mean? Okay, that before this Z alpha, how much percentage of the area is being covered. That is what it means. Okay, so if you are able to find a Z alpha such that this happens, and if you are able to relate this alpha here, so these things can be used later on when you talk about somewhere in confidence interval or somewhere. Okay, later in when you talk about the statistics part. Okay, so I'm here giving you the definition and try to give you how this is geometrically looks like. Okay, right. Now, so we have so far identified a very special type of discrete random variables named as Bernoulli, binomial, and Poisson. Then we have gone through the continuous random variables, uniform, and normal random variables. Okay. Now here is one more addition here, exponential random variable, and you will see it has some very nice property, okay, which we have not mentioned so far. Okay, and I think we have also defined the geometric random variable. Okay, so this exponential random variable can be seen as a continuous analog of geometric random variable. Okay, that you will see like we have done for the binomial and Poisson. Okay, we have related in a long run how that will be looks like. Okay, by finding that parameter lambda is equals to n time t, and we have done some mathematical or calculus things there, and we have established that as n tends to infinity, this binomial distribution tends to Poisson distribution. So similar way, okay, that you can do, you can establish the relation for the between the geometric random variable and exponential random variable. And what is the practical use of this is in the sense that it is going to give you the distribution of amount of time. Okay, so surely it's like it's like in a continuous version. So right, so for example, means like you can look at the distribution of amount of time until you receive a call. Okay, or means other things also you can look at, like distribution of time, amount of distribution of amount of time until a bulb function. Okay, bulbs are functional. Okay, means light bulbs and all. Okay, so those means like if you go little further and if you try to relate with random processes. Okay, I don't know how much you are familiar with the so far random processes or stochastic processes. So later on, you will see that Poisson process actually modeled into the exponential random variable later on. Okay, if you are going to encounter with that. Okay, right. So without making much delay, let's define the definition of this exponential random variable. Okay, so we will see also how it is going to be continuous analog of geometric random variable later on. So we say a continuous random variable x is exponentially distributed if you have the following periods. Okay, so this is lambda time e to the power minus lambda x whenever x is lies on positive axis, and it is 0 whenever x is on the negative side. Okay, so it means you can assume that x only assuming the positive values. Okay, means roughly. Okay. Okay, so okay. and here lambda is greater than 0. So which satisfies your condition that it is in non-negativity, and normality condition you can prove. Okay, you can establish the normality condition that integration over the whole line is going to be 1. Okay, and if you have encountered with the this is a very simple exercise anyhow. Limit t tends to infinity integration, you can write this, right? Lambda time limit some you have t tends to infinity integration 0 to t e to the power minus lambda x dx, and you put upper limit minus lower limit and letting limit t tends to infinity, you will get the value is 1 by lambda, and lambda will get cancelled with this 1. And this lambda also has some specific name. Okay, okay, that we will also mention. Okay, okay, now let's try to see what will be the distribution function for this exponential random variable. Okay, so we have seen this density function, so we can certainly find out the distribution function of this exponential random variable. So let x follows exponential distribution, okay, with parameter lambda. Okay, lambda is certainly greater than 0, then find fx of x. Okay, right? Now, so this implies, okay, the solution you can say. So fx of x, just follow the definition, is going to be probability that x less than equals to x. And this is going to be integration minus infinity to x fx of x dx, right? And no, fx of x is 0 for minus infinity to 0 and 0 to x. So you are talking about for, so this is equals to integration 0 to x fx of x dx, okay, and 0 if x is greater than 0, greater than equals to 0, okay, or greater than 0, that's fine. And if x is less than equals to 0, it is 0. And now I think you can integrate this now. So what you will get is this is equals to integration 0 to x lambda time e to the power minus lambda x dx whenever x is greater than 0, and 0 if x is less than equals to 0. And now this is equals to e to the power minus lambda x integration is e to the power minus lambda x by minus lambda. So you have minus common. I hope you can able to verify that's going to be 1 minus e to the power minus lambda x whenever if x is greater than 0, and 0 if x is less than equals to 0. Okay, so what it says, this implies, so this implies for x greater than 0, fx of x is, or you can say probability of x less than equals to x is 1 minus e to the power minus lambda x. And this further implies probability of x greater than x is equals to e to the power minus lambda x for x greater than 0, obviously. Okay, I hope you don't mind to change me this, okay, because you know probability of x less than equals to x is 1 minus probability of x greater than x, and you arrange the things. Okay, we are going to use this result, okay, okay, to establish a very important property and which you will appreciate later on. Okay, right. Now our next goal is to identify the moment generating function. Okay, then moment generating function derivatives, nth derivative at 0 t equals to 0 will give you the nth moment about the origin. Okay, so from there we can identify what is the mean and what is the variance. Okay, so Next, we are going to identify the moment generating function. So x follows the exponential distribution of lambda. Find mx of t. Okay, it's a very simple exercise. Okay, so just follow the definition. So you have the following solution. It's, I think, if only you have to uh, follow the definition. Expectation of e to the power tx, right? And this is equals to integration minus infinity to plus infinity e to the power tx time fx of x dx. Now this is equals to, fx of x is non-zero only between 0 to infinity. Rest is minus infinity. So this is equals to integration 0 to infinity e to the power tx time lambda time e to the power minus lambda x dx. And this is equals to lambda time integration 0 to infinity e to the power. I'm just writing for lambda minus t here x dx. Now, what can you say about this? Is this integral will converge only if lambda minus t is positive. Okay, this integral will only converges whenever lambda minus t is positive. When lambda minus t is negative, okay, this becomes positive and x is positive. So this overall this improper integral will diverge. So that you can verify. So I'm just going to give you now. This is equals to, you have, this is going to be lambda time, and again I'm going to use the similar concept for the whenever lambda minus t is positive. Okay, this is going to be lambda time 1 upon lambda minus t if lambda minus t is greater than 0 and diverges, or you can say does not exist if lambda minus t is less than equals to 0. So this will tell you that mx of t is equals to lambda divided by lambda minus t if uh, t is less than lambda. Now from here, whenever t is less than lambda, t is less than lambda, it is going to be given by this, otherwise does not exist if t is less than equals to, if t is greater than equals to lambda. Okay, now from here you can differentiate now, right, with respect to t, mx first derivative. You can find out that's going to be minus, I think, right, minus lambda by lambda minus t whole square time one more minus is there, so plus. Right, this is going to be lambda divided by lambda minus t whole square. So this will imply, let me have mx dash at 0 is equals to lambda by lambda square, that's going to be 1 by lambda. So what is mx dash at 0 is mean. So this will give you, this will imply expectation of x is equals to 1 upon lambda. Exponential random variable, you have the mean is 1 upon lambda. Now, if you go further, mx second derivative at t, because you can also find out the variance, okay, by using this. So mx double dash of t, so again you will go with this. So you have, this is going to be 2 lambda by lambda minus t whole cube with minus minus again plus. So this implies mx double dash at 0 is equals to 2 lambda by lambda cube is equals to 2 by lambda square. So now this will give you expectation of x square is equals to 2 by lambda square. Now this will imply variance of x is equals to expectation of x square minus expectation of x whole square. So this is going to be 2 by lambda square minus 1 by lambda square. So you have 1 by lambda square. So this is the variance of x. Not only that, you can see, you can from here, you can generalize this to nth derivative. Okay, it's very straightforward. Okay, the next derivative you have 2, here is 2 factorial, the next derivative is 3 factorial, and here is n plus 1. Okay, it's very simple. You can find all the nth moments here. Okay, right. So this is we have done now. Okay, so lambda is called the rate of the exponential distribution. So this is also known as the rate of the exponential distribution. Okay, right. So we have shown just now that moment generating function is lambda by lambda minus t, mean is 1 by lambda, and variance of x is 1 upon lambda scale. Okay, right? So we have shown all the things just now. Yes. So now the property which I was trying to mention at the first stage itself, okay, that it follows some certain very nice property which other distribution does not have. And the similar thing is with respect to the geometric random variable. So this property will also can be can be proved that this the geometric random variable also has memoryless property. Okay, so that we also try to do that. Okay, so here is this mathematical expression. Then we will try to address how this means physically significant it is. Okay. Okay, so we say that a non-negative random variable x is memoryless. So x must be non-negative. Okay, if you have the following. Now try to read this. What does this mean? Is if you read this t as a time parameter, okay. So what it says, this here is conditional probability. Okay, this is mean is conditional probability. Okay, now what it says, probability of x greater than t plus s, given that x greater than t is equals to probability of x greater than s. Can someone try to signify it physically? Can someone try to do that? What it means physically? By an example? Yeah. Let's take x as a random variable which give the distribution of amount of time until bulb functions, light bulb functions. So what it says that x greater than t, so at least t time it is given that the time t that functional. Okay, it has been already done that, you know, up to t time, okay, up to 30 seconds or 40 seconds, it is known that now it is given that this is till that time it was functional. Now you are again, so now you're in that case you are trying to identify what is the probability that it is still functional after t plus s time. Okay, so 30 seconds, and here is, let's say, 60 seconds. Okay, it is equals to probability that x greater than the 30 seconds. Which, like, suppose I just try to mention by example, let's say here is, let's say, 20 second, and this is here is s is here is 30 seconds, and this is here is s is 30 seconds. What it tells? Amount of time bulb function. So it is treating, means after x greater than t time is 20 seconds, 20-second time it was functional. Okay, what it is treating is after that also it is as good as it has, means if you have put the bulb, okay, as a new, okay, as a new bulb you have put on. Okay, after t time you have noted that, okay, after 20 seconds, or you can say 20 hours, okay, instead of it's physical, so 20 hours. This is 30 hours and this is 30 hours. Okay, so after 20 hours, you see that, okay, bulb is still working. In that case, you are trying to identify the probability that what is happening means, like from the starting time when you have put on the switch on the bulb, you are trying to read it after 50 hours. And what it is saying is that it's going to be same as the probability that x is greater than 30 hours. Means after t time, it doesn't matter. Okay, it is again treating that bulb as good as new. Okay, it is forgetting, or you can say it's removing that memory. So this is why it is named as memoryless. Okay, now you can further, you can use now, see, you can now use the definition of conditional probability to simplify it more mathematically. Okay, so this is here. So what is the probability of a given b? You can use that fact. So probability of a given b is probability of a and b divided by probability of b. Okay, and use that fact, and you will get an equivalent statement for memoryless property. Is that okay? So I'm just giving you here. So now look at the numerator. Okay, the right hand side is as it is probability of x greater than s. Okay, the left hand side is probability of x greater than t plus s and x greater than t. Okay, these both events happen together means probability that x, okay, greater than t plus s and x greater than t divided by probability of x greater than t. So now if you look at these both the events, okay, their intersection is what? And x is still functional t, and after it is also functional after t plus s second or t plus s hours. It's same as the probability that x greater than t plus s. And this probability of x greater than t you can shift on the right side. Okay, by means multiply both sides, because you are conditional probability x greater than t is strictly greater than 0. Okay, so probability that x greater than t plus s is equals to probability of x greater than t into probability of x greater than s. So this is another mathematical description of memoryless property. Now if you follow what we have done during the discussion of the finding the cumulative distribution function, we have found that probability that x greater than x is equals to e to the power minus lambda x. Not that x is a positive random variable, so non-negative value only assumed here. Okay, now so this is, if you follow, so if you replace x by t plus s, so this is here minus lambda time t plus s, and now you use the exponential property, and they are now individually probability of x greater than t, and this is going to be probability that x greater than s. So it satisfies the memoryless property. Okay, now you know the geometric distribution. Similarly, you try to verify, okay, that geometric distribution also follows the memoryless property in the similar manner. You find out that, okay, the cumulative distribution function for the geometric random variable, I think we have done that there. Okay, you find out that, and then you just use that fact. Okay, you have to arrange the terms in such a way, and then you are through there. Again, similar way. Okay, right. Now, so this is we have done. Okay, now the another exercise is this. Okay, so what it is saying is here is let me scalar multiple of a exponential random variable, what it will follow. So you are given with that, let x follows the exponential distribution with parameter lambda, and lambda is greater than 0. Let c is greater than 0. Then find, let me say find cx, okay, or you can say find the distribution of, find the distribution of the cx, the new random variable. Okay, c is greater than 0. So it's again, I think it is very simple. Once you take a piece of paper and pen, it's very simple. So let y equals to cx. Okay, and now you try to identify fy of y. That is going to be probability that y less than equals to y, and that is equals to probability that, simple to say, replace y by cx less than equals to y, and that is equals to probability that x less than equals to y by c, since c is positive. Okay, so this is equals to fx of y by c, right? So what it gives you the relation, so it is giving you fy of y is equals to fx of y by c. So what it tells you, this implies fy of y is equals to fx differentiation with respect to y of y by c time 1 by c. Okay, now that you can now go for this, now 1 by c time c is positive, so you have this is going to be lambda time e to the power minus lambda x, right, lambda y by c. Okay, whenever y is greater than 0, greater than 0, and 0 whenever y is less than 0. Now you can see lambda by c here and lambda by c here, you can collect both the things. So lambda by c becomes a parameter. Okay, c is also greater than 0 and lambda by c, lambda is also greater than 0. So this will tell you together that y follows, okay, y follows the exponential distribution with parameter lambda by c. Okay, right. Now let's, I think we have one example now. Yeah. So try to read this example, which says that suppose that a number of miles that a car run before its battery wears out is exponentially distributed with an average value of 10,000 miles. Okay, so it's straightforward. It is giving you that its battery wear out is that that a car can run before its a number of miles that a car can run before its battery wears out is exponentially distributed with an average value of 10,000 miles. So battery will function, okay, exponentially, okay, or you can say the time, amount of time until battery functional is exponentially distributed. Okay, in terms of thousand of miles is 10,000 miles now. Okay, that is a average value, okay, of exponentially distributed. Okay, now if a person desires to take a 5,000 miles trip, what is the probability that she will be able to complete her trip without having to replace her car battery? So it's given to you that battery is the time, the amount of time until battery wears out, okay, or until battery functional is exponentially distributed with an average value of 10,000 miles. So let us have x as a remaining lifetime of the battery in 1,000 miles. Why we are taking as a remaining time lifetime? Because We don't know how much time it has already functioned so far, but it is given that that is exponentially distributed. And since exponential distribution is a memory less, so it will again treat that at battery as new as good one. Okay. So with that information, we have X as a remaining lifetime of the battery, which will run in thousands of miles. So expectation of, sorry, not this exponential of lambda value. What is the lambda value? So it is given that the mean, okay, expectation of that X is 10,000 miles. So in 1,000 miles, it is 10. Okay. Now this is implies 1 by lambda equals to 10. So this will give you lambda is equals to 1 by 10, and this will do equal to 0.1. So that X will follow the exponential distribution with parameter point lambda equals to 0.1. Now, what you are interested in, if a person desires to take a 5,000 miles trip, so certainly battery should function more than 5,000 miles. So therefore, you are interested in finding the probability of X greater than 5. And if you recall, probability of X greater than T is equals to e to the power minus lambda T. So you have to just replace T by 5, and lambda value is 0.1. So it's going to be approximately probability is e to the power minus 0.5. Okay. Right. Now, I think I have this exercise, and which is going to be very important. Okay. You will see one example we will also have where it is very much required. Okay. So, if you have n number of independent exponential random variables, then if you take the minimum, so because exponential random variable most of the time tends to the distribution of amount of time until certain being functional, you can say. So you require the minimum time that complete system will function. Okay, means where different components will be there, and which suppose by any chance that all of them are exponentially distributed. So you can actually decide up to what minimum amount of time it will function. Okay, so that till that time, or you will get a period of amount of time in hand to get another stock. Okay, for the same. Okay, to call for a stock for that those components and so on. So see, this is y equals to, so this is a, we have defined the minimum of x1 to xn, and what will be the distribution is going to be nothing but the again exponential distribution with the parameters summation is lambda is. So what we can do here is we can take the help of distribution function. We know, okay, how to handle that. So if you try to see here, so try to see the solution. Okay, fy of y is equals to, you have a probability that y less than equals to y. Now I think let me have, this is y, probability of y less than equals to y, and if I write here minimum of x1 to xn less than equals to y. Now if we start in this fashion, it will not work. Why? Because if it is maximum here, then we can have each xi is less than equals to y, but it is minimum. So some of them can go beyond y. So instead of this picture, what we will see is the negation of it, okay, or 1 minus of that. So in that scenario, if I try to work out this probability of y greater than y, okay, I'm going to work out with this probability. Then later on, you know, this is going to be related with this 1 minus probability of y greater than y, right? So how it will help you is, this is going to be probability that minimum of x1 to xn greater than y. And now see, minimum is greater than y means each xi is greater than y. So it's going to be probability that x1 greater than y, x2 greater than y, and so on, xn greater than y. And now since all of them are independent, so this is going to be product of I is equals to 1 to n, probability that xi greater than y. Now each xi is exponentially distributed. Okay, so each xi follows the exponential distribution with lambda I. Okay, I is equals to 1 to n. So then probability of xi greater than x is equals to, e to the power minus lambda ix. So if you use this fact, this will together will give you probability that y greater than y is equals to product of I is equals to 1 to n. Probability that xi greater than y, that's going to be e to the power minus lambda I y, and that is going to be equals to, now you use the minus summation I equals to 1 to n lambda I y. So this is equals to, you can denote this by lambda e power minus lambda y. Okay, and which says that again y will follow, this will implies y follows exponential distribution with parameter lambda, where lambda is summation of I equals to 1 to n lambda. Okay, right. Now we have done this. Okay. Okay. So now this problem you look at. Okay. So it says that a series system is one that needs all of its components to function in order for the system itself to be functional. Okay. For an n component series system, so there is an n component series system in which the component lifetimes are independent, exponentially distributed random variables with respect to parameter lambda 1 to lambda. What is the probability that the system survives for a time t? Means system will survive at least time t. Okay, means minimum of, so again you have to see, if you say each component will correspond to the xi random x means x, each ith component correspond to xi random variable, the lifetime of nth ith component. Okay, so if you say okay, xi denotes the lifetime of, or remaining time, whatever, so lifetime of ith component. Okay, so this will for certainly follow exponential distribution with parameter lambda I. And now you want the system will survive, the system will function whenever all of them together functional, all components should function. So minimum of them we have to work for. Okay, all should work together. Okay, so this is why here, okay, so you are going to work with y equals to minimum of x1 to xn, which will follow the exponential distribution. Just now we have seen summation of lambda I is equals to 1 to n. Okay, and what you are interested in is probability that y greater than t. That's going to be e to the power minus lambda t. Just now we have found. So lambda equals to summation lambda I is equals to 1 to n. So now you can, if you have the value of lambda i's and you have the time t, you can actually find out the probability there. Okay, right. Now, so now the generalization of, or you can say a new distribution which is known as gamma distribution, for which this exponential distribution becomes a particular case. Okay, why it has come into the picture, that you will see later on, that if you take an independent exponentially distributed random variable and if you try to look at the distribution of their sum, okay, that will follow the gamma distribution, okay, that you will see. Okay, right. So I hope you are all very much familiar about the gamma function. Okay, if I want to mention here, it is gamma alpha is equals to, you have integration 0 to infinity x to the power alpha minus 1 e to the power minus x dx. If you recall, and you, of course, here is alpha is greater than 0. Okay, so you can also look at on this probability density function. So here is, there are two parameters, alpha and lambda. Okay, for gamma distribution you have the two parameters, alpha and lambda. Okay, so here, this why here's notation is x follows gamma with alpha comma lambda. So you need both the parameter to define this gamma distribution. Now you can look at, so what is the additional multiplication of exponential? So lambda time e to the power minus lambda x time lambda x to the power alpha minus 1 divided by gamma alpha. Why it has come into the picture, you can look at here. Okay, so what you can do is, here is, you can substitute x equals to lambda y. Okay, you can substitute, so you can say now see, gamma of alpha is equals to integration 0 to infinity x to the power, instead of x I'm taking another variable, let's say y to the power alpha minus 1 e to the power minus y dy. Let's take y equals to lambda x. Let's take y equals to lambda x. So implies dy equals to lambda dx. Now, y equals to 0. So obviously lambda is greater than 0. I'm talking about lambda is greater than 0. Y is equals to 0, lambda x is also 0. Okay, y is tending to infinity, x is also tending to infinity. So limits will remain unchanged. Okay, so this will imply gamma alpha is equals to integration 0 to infinity lambda x to the power alpha minus 1 e to the power minus lambda x dy is now lambda dy. Okay, now if you arrange everything, this will imply 1 equals to integration 0 to infinity, you have lambda time e to the power minus lambda x time lambda x to the power alpha minus 1 divided by gamma of alpha dx. So this is nothing but that your density function. Just now you have defined this one. And so this is satisfying that normality condition. Okay. Now let's try to show that this task. Okay, I will come back here. Okay, let's try to find out its moment generating function. Okay, then we will see how it is. So it is very simple to follow from here, that alpha equals to 1 will give you the gamma distribution. Okay, sorry, alpha equals to 1 will give you the exponential distribution, right? Alpha equals to also 1 minus 1 0. Okay, and you have gamma 1 is 1, so you are only a lambda time e to the power minus lambda, which is very well that is going to be a distribution function for density function for exponential random variable. Okay, now if you try to, so let me find out the moment generating function, find MGF of gamma distribution alpha comma lambda. Okay, right. So mx of t is expectation of e to the power tx. Again, you have to use carefully everything. Okay, that's going to be integration minus infinity to plus infinity e to the power tx fx of x dx. Now see, it's non-negative, it's 0 from minus infinity to 0, so it's going to be integration 0 to infinity. You have e to the power tx time, you have lambda time e to the power minus lambda x, and you have lambda x to the power alpha minus 1 divide by gamma alpha dx. Okay, now this is equals to lambda by gamma alpha. Lambda is out from here, and lambda to the power alpha minus 1 is out, so lambda to the power alpha is here. Okay, and what is remaining is integration 0 to infinity x to the power alpha minus 1 time e to the power tx minus lambda x. So I am just writing it t minus lambda x dx. Now you can further because it looks like that lambda alpha by gamma alpha integration 0 to infinity x to the power alpha minus 1 e to the power, I'm taking minus out, and what is remaining is lambda minus tx dx. Now what you do is substitute. Okay, substitute is y equals to lambda minus tx. Okay, so whenever x is 0, again, so you are taking only the case where lambda of this lambda minus t is positive. Okay, else I think it is going to be decreasing. Okay, divergent does not exist. So we are only considering the case when lambda is greater than t. Otherwise, this improper integral will diverge. So once you have this substitution, so what you will have is mx of t is equals to lambda to the power alpha by gamma alpha integration 0 to infinity. Now x is y by lambda minus t, so you have y to the power alpha minus 1 divided by lambda minus t to the power alpha minus 1 e to the power minus 5, and what is dx is dy divided by lambda minus t. And now if you further simplify, this is equals to lambda to the power alpha by lambda minus t to the power alpha 1 upon gamma alpha time integration 0 to infinity y to the power alpha minus 1 e to the power minus y dy. And this is 1. So this is going to be lambda by lambda minus t to the power alpha. Why it is this? Why I have found this moment generating function for gamma distribution is to find out the distribution for to relate it with the exponential distribution. Okay, so alpha equals to 1, you can see for alpha equals to 1, it's a moment generating function for exponential distribution. Okay, now let's take an exercise now. Let x1 x2 and so on xn be independent independent uh, uh, exponential random variables with variables with lambda I is equals to lambda for each I. Okay, I is equals to 1 to n. Then their sum x1 plus x2 plus and so on xn will follow the gamma distribution with parameter n comma lambda. Alpha equals to n and lambda equals to lambda. So here we will take the help of moment generating function. Okay. So for this solution, so let y equals to x1 plus and so on plus xn. Then my of y is equals to expectation of e to the power ty is equals to expectation of e to the power t time x1 plus xn. Now here I know, I think you can easily follow that it's going to be product of I equals to 1 to n e to the power t xi, expectation of e to the power t xi. So moment generating function of each xi. So we have already seen that lambda by lambda minus t, right? For exponential distribution, the moment generating function is lambda by lambda minus t. So it is n time. So you have lambda by lambda minus t to the power n. Obviously, lambda is greater than t here, or t is less than lambda. Okay, so this will tell you, this is very straightforward now from here. Y will follow the gamma distribution with parameter n and lambda. Okay, right. Now, this gamma distribution is also related with the very important distribution which you are going to learn in the, or which has the high use in this statistics. Okay, chi-square distribution. Okay, so you will see there also you will be encountered with the gamma distribution. Okay, keep in that mind. Okay, so this is why it is important to introduce. Okay, so we have done all these things. Okay, right. Now here this picture is for gamma distribution. Okay, for a fixed lambda. So lambda is fixed lambda, and alpha is varying. Okay, now you can see alpha equals to 0.5. This is the curve. Alpha equals to 2. You have the this curve is there, right? Now alpha equals to 3. So you may later on learn, maybe somewhere, that positively skewed or negatively skewed later on. Now alpha equals to 4. You have this one, and alpha equals to 5 is this. Can you tell me what will happen if you go for more increasing alpha? Alpha equals to, let's say, 10 or 20. So where this curve is tending to? If
Sir,
alpha is increasing, huh?
Sir, I think to uniform distribution as alpha increases.
Uniform. Do you recognize uniform distribution is like if you have, is a line. Is it parallel to x-axis? No. it will go towards the bell-shaped curve, means normal distribution. Okay, and that's what is the base here? Mathematical base will also come into the picture. Okay, that is named as the central limit theorem, which tells you that you take any distribution, if you increase the parameter values, okay, if you keep on increasing the values, it's going to be all at the end, as in the long run it can be approximated by using the normal distribution. Okay, you can see previously it was you can say positively skewed. Now it's going to be now more towards, like, see, this is here is now very less skewed here. Okay, now later on I think I have this is here is for alpha equals to 50 it is. Okay, it's going like this. Okay, okay. Now I have I think so we have already
Yes, sir.
find out the gamma distribution. Huh? Yeah.
Sir, what is the x axis in this? Yeah.
X axis. What is the?
Like what has been plotted on the x-axis? Like it's only random
So this is
numbers
the
or
x
it is
axis. This is x axis. Alpha equals to 50. Lambda is some fix. You can fix some number 1 or 2 or 3, any number. Okay. What you can do is, okay, here I can I think you are familiar with MATLAB.
yes,
You
sir.
know how to use a MATLAB? Okay. So there are well-defined gamma distribution functions. Straightforward gamma distribution function is there. Okay. And you know that how you can, I think you know very well that how to plot in a MATLAB. It's very easy. Okay. You can take that exercise. Okay. It's
Okay, sir, I'll
very
check it out. Thank you.
uh,
I'll
okay.
check
So
it out.
gamma distribution, exponential distribution, normal distributions, or are well-built library in the this MATLAB. Okay, so there you can see how the parameter varies. Okay, and you try to plot. So you see, this is a plot for the density function. Okay, so density function means you have a x here and you have a fx of x. This is x, fx of x, and this is x here. Okay, x y you can say, and this is a curve that fx of x will give. Okay.
Okay, sir.
Right. So now see, for the gamma distribution, you already identified what is the moment generating function, and you know it is very easy to identify the nth moment by differentiating it. Okay. You can find out its mean and its variance easily. So that I can leave as an exercise to you. Okay. So this is again, it will involve the mathematics here. So here is, I think I may give you. So this is you know the relation. Okay, you can use this relation to identify the mean and variance. Again, you have to differentiate with respect to t and evaluate at t equals to 0. Use that fact and you can find out. Okay, right. Okay, now what will happen if you take two gamma distributed functions? So it's again again in the similar fashion. Okay, once if you in the similar fashion means sum of two independent gamma distributed random variable where the second parameter is remaining fixed, lambda is fixed, only varying is alpha is. So you will again sum will also lead to the gamma distribution. Okay, so again you will take the help of, because here is whenever you have independent random variables and you are trying to identify the distribution of sum, what is the immediate, I mean from which you will take the immediate help is moment generating function. Okay, because you can use the independence of the random variable easily and you know individual distributions, so it will clearly identifies sorry, that the sum of two independent gamma distributed random variables is again gamma distribution. Okay, and provided here is lambda is fixed, keep in that mind. Okay, so if lambda also vary, you have right lambda 1 here, lambda 1 by lambda 1 minus t, and lambda 2 by lambda 2 minus t. So which will not identify the gamma distribution. Okay, here lambda is fixed, only alpha is varying. Okay, okay. So this is already I have done. This exercise is already done. So if you have n independent exponential random variables, this is a very, see, from if you followed this, it's very simple. So because alpha 1 and alpha 2 here is, if you take 1, it is gamma. A gamma becomes a exponential. So if you take 2 gamma, 1 plus 1 here is 2 comma lambda. If you take n, you will have n. Okay, you can generalize this to that, or we have already established this result. Okay, right. Now, so here it is, means like it's this example is can be understand once you read it. So what it says is the lifetime of a battery is exponentially distributed with rate lambda. Okay. Now, if a stereo cassette recorder requires one battery to operate, okay, then the total playing time one can obtain from a total of n batteries. So n batteries is storage, you can say, and you can keep on playing the stereo cassette recorder. Okay, and each battery follows exponential distribution with rate lambda. So total playing time will follow the gamma distribution with parameter n comma lambda. So this, it's very simple heuristic example of where the gamma distribution is occurring. Okay, right? Now let me define this chi-square distribution, then we will close this session. Or okay, we will start for the chi-square distribution in the next time. That's fine. You can that recorded lecture which I'm going to put on the YouTube, that actually have this chi-square distribution. So from there also you can learn before coming the next lecture. Okay. If you have any question, you can ask.
Sir, when will be the Moodle exam conducted?
Yeah, this week, this weekend I will announce. Okay, most probably on 13th of March. So, okay.